The modern AI infrastructure build-out requires linking tens of thousands of GPUs together to train a single model. At a cost of around $30,000 per chip, a typical data center deploys hundreds of millions of dollars in capital just to execute one distributed training job. The primary bottleneck limiting the return on that massive investment is the network fabric connecting those chips. In production clusters, communication bottlenecks consume between 16 and 50% of the total training time. Hyperscalers measure this efficiency through model flops utilization, or MFU. This metric tracks exactly how much theoretical compute is converted into real mathematical training work, rather than lost to communication overhead. At 40% MFU, a 10,000 GPU cluster wastes 60% of its capacity, nearly $200 million annually consumed by idle processors waiting on the network. Maximizing MFU is critical. Every 10-point improvement recovers roughly $30 million in annual GPU value. Distributed AI training relies on micro-level synchronization. Thousands of times per second, processors must execute collective operations, exchanging gradients and parameters in a highly choreographed sequence. Because this process is strictly synchronized, the entire array can only advance as fast as its slowest connection. A single delayed network packet creates a system-wide stall, known as the straggler effect. This failure cascades instantly. One delayed message at a single switch forces thousands of waiting GPUs to halt their calculations and idle simultaneously. These stragglers are often rooted in equal-cost multipath routing, or ECMP. This is the load balancing mechanism designed for the high-entropy traffic of the web, not the synchronized demands of AI. Unleashing the capacity of a GPU cluster requires moving past the probabilistic limits of internet routing toward a predictable, deterministic network fabric. ECMP operates like a mail sorter. It reads 5 key pieces of header information on an incoming packet and runs them through a mathematical hash to distribute traffic across available paths. AI training creates a very different traffic profile. It generates massive, continuous data streams called elephant flows that saturate network links at full line rate for extended durations. Because GPU to GPU communication frequently uses the same protocols and ports, the ECMP hash often calculates an identical result for multiple elephant flows. This logic failure is known as hash polarization. The physical result is a massive traffic collision. The switch pins multiple heavy flows to the exact same output port, jamming that link while an adjacent pathway sits empty. This congestion is the mechanical origin of the straggler effect. Applying probabilistic hashing to a rigid, synchronized communication pattern results in predictable systemic failure. Current industry responses, adaptive routing, flowlet switching, and packet spraying, attempt to resolve these collisions after they form. These solutions share a reactive logic loop. They must detect congestion, decide on a new path, and then respond to the bottleneck. At AI speeds, straggler cascades happen within the window of detection. By the time an adaptive routing system reacts, the GPUs have already entered an idle state. Flowlet switching requires natural idle gaps between data bursts to reroute traffic safely. AI elephant flows are continuous streams with no idle gaps, which breaks the flowlet detection logic. Packet spraying bypasses the hash by scattering packets round-robin across all links. However, delivering packets across multiple paths with varying delays guarantees they arrive out of order. These out-of-order packets create buffer pressure at the receiver, which eventually triggers priority flow control pauses that propagate congestion back through the entire fabric. Eliminating stragglers requires a system that prevents congestion from forming, rather than one designed to respond to it. The Predictive Tensor Control Plane, or PTCP, is a hardware-agnostic software overlay that maps and manages network paths using geometric principles. Pillar 1 is the topographic model. Traditional routing treats the network as a flat, abstract graph, assuming all paths with an equal hop count are identical. PTCP builds a model of the network's physical reality. It accounts for cable lengths, switch buffer depths, thermal zones, and power domains, creating a navigable terrain of capacities and bottlenecks. Pillar 2 involves geodesic route calculation. Just as a geodesic is the shortest route across a curved surface, PTCP computes mathematically optimal paths that account for the topographic curvature of the data center. This allows the system to route around predicted congestion zones that ECMP would cut into blindly, because it only sees a flat hop count. Mapping the true structural geometry of the data center is necessary to find the globally optimal path for a synchronized training job. Pillar 3 is deterministic enforcement. Once a geodesic path is calculated, it is strictly applied to the traffic flow. PTCP abandons the probabilistic sorting of ECMP and instead pre-assigns strict routes for elephant flows before transmission begins. This deterministic approach eliminates the possibility of hash collisions. The risk of flows being accidentally pinned to the same link is reduced to absolute zero. Because paths are fixed and pre-assigned, packets arrive in perfect order. This removes the need for receiver-side reordering buffers and prevents the pauses that slow down the training run. By pre-computing routes based on data center geometry, the system prevents congestion before it forms, removing the need for a detection loop. When the network is no longer a source of synchronized delays, the GPUs spend more time on matrix multiplications, and MFU is maximized. Synchronizing the network fabric reclaims tens of millions of dollars in wasted GPU value, ensuring the cluster operates at its theoretical peak. This gap between hardware capacity and actual execution exists across several critical path industries. In semiconductor design, the fastest EDA tools still face an infrastructure tax, where jobs wait for license features, data locality, or storage metadata. PTCP addresses this by acting as a cross-layer overlay. It coordinates compute placement, license admission, and storage QoS to prevent these uncoordinated delays from stalling the tape-out schedule. In high-frequency trading, infrastructure variance can fatally dilute the value of an alpha signal between its discovery and its execution at the venue. By providing a unified control plane, PTCP preserves trading intent and reduces path variance, keeping the entire research-to-market system inside a verified operating envelope. AI, semiconductor design, and electronic trading all suffer from the same pathology, the failure of isolated components in a deeply coupled critical path system. Gains from faster GPUs, NICs, and switches are diminishing as the coordination gap between those components grows wider. Managing these systems requires a shift toward a unified, predictive software control plane that views the entire facility as a single machine. Eliminating infrastructure variance ensures that billion-dollar clusters spend their cycles on training logic rather than recovering from avoidable network stalls. Elite distributed computing will be defined by deterministic coordination, turning a collection of fast hardware into a single synchronized machine.